An energy distribution curve describes the energy of the particles in a given sample. On the y-axis, we have the number of particles, and on the x-axis, we have the amount of kinetic energy those particles have. The instructions under the curve say to draw a line down the middle that represents the activation energy, or the amount of energy required for the reaction to occur. Right now, most of the particles have less than that minimum amount of energy they need to react. So what we're going to do is shade in the area that represents the particles that do have enough energy to react. Increasing the temperature increases the number of particles with enough energy to react. So the instructions say to draw a new curve that represents when the temperature is increased by 10 degrees Celsius. Increasing the temperature by just 10 degrees doubles the number of high energy particles that have enough energy for a reaction to occur. So we're going to show that by shading in the new area that represents the number of particles with that activation energy. Catalysts increase the rate of a reaction without undergoing any permanent change itself. They do this by providing an alternative pathway with a lower activation energy. Now, if we were to draw this on a potential energy diagram, the activation energy, or EA, would be lowered. And the reversed activation energy, or EA reverse, would also be lowered. But notice how the energy of the reactants at the beginning of the reaction and the energy of the products at the end of the reaction stays the same. That means that the overall delta H for the reaction will stay the same as well. If we were to draw a lower activation energy on an energy distribution curve, it would increase the number of particles with enough energy to react.